Okay, hi everybody. It's Samantha. I'm one of the Chem001C SIs, and I SI for Dr. Dean Jang, Section 1. My email and my office hour sessions are down below if you have any more questions outside of this video. So please feel free to reach out. Today we're going to go over aqueous equilibrium, and in particular, we're going to go over 15.1 and 15.2, acids and bases, and acid strength and molecular structure. These were covered in Monday's lecture with Dr. Jang, but I hope if you have a different professor for Chem1C that this is still helpful. So before we start, let's first go over aqueous equilibrium in particular. We've done a lot of chemical equilibrium so far, but as we start chapter 15, we're going to redirect our focus to aqueous equilibrium. So when we're looking at aqueous equilibrium, we're going to look at aqueous solutions. And what exactly are aqueous solutions? If you look at the word aqueous, if you can take a wild guess, we're going to be looking at solutions that involve water. So when we're looking at aqueous solutions, we're looking at aqueous solutions in equilibrium. So hence aqueous and equilibria, aqueous equilibrium. So as we get started, we're going to go to 15.1, acids and bases. And if you recall from lecture, Dr. Jang covered two particular types of acids and bases. And what were those? Well, those were Bronsted-Lowry acids and bases and Lewis acids and bases. Now, what makes the difference between those acids and bases? Let's start to cover that. So a Bronsted-Lowry acid and a Bronsted-Lowry base, what's the difference? So an acid is going to do what? That's right, an acid is going to donate a proton. So if you look here, that's what it says, and a base is going to do what alternatively? Because they're just opposites, right? It's going to accept the proton. Now, that's the definition he gives us for Bronsted-Lowry acids and bases, but what's the definition that we have for Lewis acids and bases? Well, a Lewis acid and a Lewis base, an acid is an electron pair acceptor, and a base is an electron pair donor. So denote the difference. You want to be able to tell the difference so that you don't confuse that on an exam. You don't want to say that an acid is going to accept a proton because that's wrong. It accepts an electron pair. So remember the differences, because for a Bronsted-Lowry acid and base and a Lewis acid and base, it kind of switches what donates and what accepts, right? So make sure you know the difference, because that's going to be important in the next part. So with acids and bases, we're not always going to just be going over verbally what it is, right? But we want to know with data in labs how that's going to look. So how do you measure acidity and basicity? Well, if you remember from Dr. Jang's lecture, he had that little chart with the 4 arrows, and you want to be able to calculate pH, pKa, and pKb. So I put pH and pOH here because they're really important to understand the difference. pH, if you look at the equation, pH is equal to what? Negative log of the concentration of H protons in solution, in your aqueous solution. And pOH is equal to the negative log of OH in solution. So why is it important, and what's the difference between pH and pOH? Well, pH and pOH, they're really similar because they both tell you about the acidity or basicity of your solution. If you're given the concentration of OH, you're going to be looking at it on a basic scale. If you're looking at pH, you're looking at it on an acidity scale. So pH is the one that we commonly know, right? A low pH means it's acidic, and a high pH means it's basic. pOH, because you're looking at it on a basic scale, is the opposite. A low pOH means that it's basic, but a high pOH means that's acidic, and that's why I put it over here. So you just have to think what's on the opposite end, right? If acidic is on one end, that means basic is on the other end. The other equation he gives you is pKa and pKb. I didn't put pKb here because, like much like pH and pOH, they're just the opposite, right? Acid strength is denoted by pKa, and base strength is denoted by pKb. So let's look at acid strength here. pKa is equivalent to negative log of Ka. And the important trend to know there is when you have a low pKa, it means it's a strong acid, much like pH. So pH and pKa are going to be similar. If a pH is low, it means it's acidic. If a pKa is low, it means it's a strongly acidic substance, so it's a strong acid. But what happens if your Ka is high or low? If you have a low Ka, you have a weak acid. Okay? But what happens if you have a high Ka? What happens then? That's right, you have a strong acid. Okay. Now, how does this actually apply? A lot of times in science, it gets kind of confusing because you don't really see its actual application in the real world. But let's look at some examples of acids and bases that we commonly see in daily life. So if you look at acids and bases, there's a lot of acids and bases that you see around you. You see it in vinegar, lemons, oranges, HCl. Those are all different types of acid. So you have acetic acid in vinegar, citric acid in lemons, and hydrochloric acid, HCl, in your body. You have that a lot in your stomach, the gastric acid, because you need it to help digest and break down your food. So those are some kinds of acids you see in real life, and it's important that it doesn't become too acidic or too basic. Now you can also see bases in real life. You'll see it in baking soda, soap, and toothpaste. So baking soda you commonly use when you're baking, when you're cleaning. Same thing with soap and toothpaste, right? So those are just some examples that I thought were cool for you guys to kind of see that it is everywhere around you. And let's head into the next topic, 15.2, acid strength and molecular structure. So acid strength is what he covers. He'll go over basic strength, I believe, in the next lecture. But let's first talk about the types of acids. So you're going to be looking at inorganic acids and organic acids. For this class, you don't really need to know the difference in strengths between organic acids. He mainly focuses on inorganic acids. And within inorganic acids, there's two different kinds, right? There's binary acids and there's oxoacids. Let's take a little bit of time. I'll give you guys a few seconds. If you look at binary acids and oxoacids, what's the difference? Why is it a binary acid and why is it an oxoacid? If you've caught it, let's look at binary acids first. So look at the word binary, right? When you think of bi, it means two. When you look at binary acids, it's easy to tell that they're binary acids because there's only H and one other thing. So there's only two, essentially, elements from the periodic table. So there's, in this case, for HCl, there's only H and Cl, and so on for those. If you look at H2S, is that still a binary acid? Yes, it is, because there's only H and sulfur. There's only your proton and the sulfur. So there's only really two things. That's why it's a binary acid. Oxoacids, on the other hand, are a little bit more complicated. You have molecules that have more than three elements, or sometimes just three elements. So that's important to note, the difference between binary acids and oxoacids. Because when we look at the trends, it becomes harder to predict the strength, right? Now, before we head into the next topic, or the next trend, can you guys predict really quick which would be more difficult to tell the strength of, which are going to be easier to use, or which is going to be easier to predict a trend in? So let's start with acid strength for binary acids. So for binary acids, there are two things you really want to look at, and that's electronegativity and atom size. On the chart on the right, you have atomic size and electronegativity and ionization energy trends. Let's start with electronegativity. So as electronegativity increases, acidity increases. If you look at the black arrow on that chart, that's your electronegativity trend. So why is it that as electronegativity increases, acidity increases? Well, it's because the higher the electronegativity is, it creates more of a polar bond, so it's easier for that molecule to donate the proton it's attached to. If you remember, electronegativity, what does electronegativity mean again? It's that, for example, if you have H and Cl, Cl is, if you look at your trend, it's an electronegative molecule. So an electronegative molecule means it wants the electrons. It's electronegative, so it's hungry for the electrons, right? Because it creates that polar bond, because it wants the electrons, it makes it easy for H to be donated, because it doesn't have such a strong connection between the two. So that trend goes up this black arrow and then right that arrow, right? So it goes up and to the right. That's your electronegativity trend. But what happens if the electronegativity, for example, let's look at our halogens, so fluorine, chlorine, bromine, iodine. What happens if these all have a similar electronegativity? Can you tell the acid strength can you tell a difference between the acid strength of those molecules? It's a little bit more difficult, right? So what you look at then is you look at the size. As atom size increases, acidity increases. Why is that? Well, let's look at the atomic size trend. So it's going to be this red arrow. As atomic size increases, acidity increases. And that's because if you take a larger molecule, let's compare Br and Cl, right? HCl and HBr. Which of the two is larger? HBr is larger, right? Based on that red arrow's trend. So if HBr is longer, its bond to the H, the Br to the H, that creates a longer bond because it's a larger molecule. So the radius of the H to the radius of the Br, that bond distance is larger than that between H and Cl. So let's see if I can annotate really quick. Okay, this is my Br, right? And this is my Cl. The bond distance between the middle of each, the HCl creates a shorter bond than that of HBr. And if you remember from previous chem classes, a longer bond is easier to break, right? It's like if you take a long stick, and you break it in half, it's easy that first time. But if you try to break it again, it becomes a little bit harder, right? As it gets shorter, it gets harder and harder to break. The same thing with the bonds between these molecules. The longer the bond is, the easier it is to break. The shorter the bond is, the more difficult it is to break. So in terms of acidity, if it's harder to donate that proton, it's not going to be such a good acid, right? So it's not going to be as strong an acid. Okay, so let's go to the next slide. So that's how you determine acid strength between binary acids. Now, how do you do it? How do you do it with oxoacids? Well, with oxoacids, because you don't have just two things, you have multiple things. In this case, you're going to be looking at your oxidation number. And oxidation number you guys should have learned that last quarter. But if you look at this example between HClO4, HClO3, HClO2, and HClO, The higher the oxidation number, the more acidic. So that's our rule, right? In this case, it already has the right trend. So if you look at HClOs, 4, 3, 2, and then 1, if you look at these three molecules, HClO4 is going to be the most acidic, right? And why is that? It's because it has the higher oxidation number. It has the most number of oxygens, so you know that this has to have the highest oxidation number, okay? And that's going to help you determine what's most acidic. Now, what happens if, just like with binary acids, what if they have the same thing, the number is the same? Well, in that case, you go back to your electronegativity. Now, what's more electronegative? It's the same trend as with binary acids. As electronegativity increases, your acidity increases. And I want you guys to answer why that is. If you need a little help, hint, hint, it was explained with binary acids. It's the same exact reason. That's it for today. I hope all of that was helpful. If you have any more questions, please comment down below or email me. Or if you have more questions, please feel free to join my office hour sessions that were at the start of this video. Once you finish, please don't forget to sign in the link down below.